Alright, here we are. This is the 4-pole again, running without the MIC coil. And we're running a 100-watt light bulb here off of an inverter, so that's about 120 watts because the inverter is only 80% efficient. So I have it swapping every 5 minutes just as a test. And what we're going to do is just go over some of the details. So of course I've got to change my amp meter every time it swaps. So we're at 3.5 amps and we're producing 100 watts of light, more or less. I haven't checked the voltage on it, but DC voltage, or sorry, modified sine wave. So there, okay, so there it's switched. So this battery is more fully charged. So normally what we would have is starting off with the charged battery and running that for at least an hour or so, depending on the size of the battery. And then the other battery would fully charge up. In this case, I started with a discharged battery and a charged battery, and after 5 minutes, obviously it didn't fully charge. So it's 3.5 amps, and you can see that here. Not sure if I can get that. 3.5 amps there. And what we have is on the output side, really not good clips here. Clip lead. Anyway, the point is I just wanted to get it running in the basic mode. And you have to really be careful with this Paul switch. And I'll bring the camera over later on here to explain that. So we're using clips, and we shouldn't be. We should be using solid connections. So all these connections need to be changed, but this is how I send out the kit in the basic mode. So these are they're not making very good contact. And so what we have here is the generator coils in series, and they are charging this 12-volt battery, and it's sitting at 1167, 68, and then the inverter is running off of that battery, and I have 60 microfarad worth of capacitors across the AC side, the input side. So across the generator coils, I've got 60 microfarads worth of capacitance. Unless some of them aren't necessarily connected here. So I have to balance that out. The more capacitance we put on this, and the more it's drawing, the more it will draw down the motor. So if I have, there's kind of a limit to it. And again, I should be using better wires and connections here, but just doing what I can do here. So I want to also deal with the hall. See if I go a little bit to the right. It's right about where it wants to be right now. And so really I should be using an 80-watt bulb, and I just thought I would try the 100-watt for now, and we can look at 60-watt right here, and well, we want to see the voltages first. So if we look at the voltage, so we're up there 108.5 volts, which is right for the DC, or sorry, modified wave inverter. So now it's switched back, and we're drawing about about 3.5 amps still. Anyway, what we're going to do is go down because it's a little bit more than it needs to be. Unfortunately, I can't unscrew this very well. It's hot. So this is just your really cheap inverter here. Just running it as a basic test. Let's see if get that in the camera. This goes back like 25 years on that inverter, I think. Oh, hot bulb. So I'm gonna, sorry. Here's the bulb right there. It's Philips. I'm not trying to prove anything here, but this is actually for a customer. And so we're going to look at this 60-watt bulb here. And so of course the voltages have gone up on the charged battery, the accessory battery, I guess you could call it the load battery. So now let's look at the voltages again. Should be maybe a little bit higher. Oh, it's still about the same, 106.3. So that's what the inverter wants to put out, which is a modified wave, so it's going to be lower. So then we want to look at some voltages here, just to make sure everything's good. So these batteries are charging up. This one is lower. This is the run battery right now, I believe. Yeah. So this one under load is 11.75. So this is really kind of where it wants to be. 11.75 on this battery. And that's really where it wants to be. Because when we think about it, if we're drawing, let's see, like right now, we are running it at 11.75, was it? Times 3.6 amps around. So that's only 42 watts. And actually it's not even quite accurate because some of the energy is coming from the charging battery as well to run the system with this type of motor arrangement with our capacitor. And so so forth. So for 42 watts, we're actually producing, we're being able to rotate the batteries around every 5 minutes. And now we're running continuously about 80 watt load right now. So I wasn't expecting to do that. I was expecting it to be about equal. So that's quite interesting. So I'm not going to be exactly accurate here. I'd have to test this over a long period of time to give you the exact numbers. But all I was hoping for is producing about the same amount of output as the input. Sorry, this board is kind of making a noise here. Let me take care of that here. Some bit of foam or something. I'll put there. All right, so now it's switched over again to the faster battery, the more charged battery. So this is really where it would want to be. This is how it would normally be running. Gotta zero this out all the time. So 3.5 amps, and now we're looking at $12.45. So that's pretty much what I wanted to cover. So I'm going to bring the camera over so you can see this in detail. All right. All right, so let's look at this now. This is just to deal with that vibration on the board. Okay, so we're sitting at 1171 on this battery here, and I've got a 50 amp bridge rectifier here. So we've got the generator coils. Generator coils are coming out, going to this bridge, and we've got all these capacitors across the bridge here. It's kind of a mess because I wasn't sure of what I was doing here in regards to the amount of capacitors here. And these are AC caps because it's on the AC side. And then I've got these funky little wires here coming off going to the charging battery, and I'll be putting thicker wire on there and making solid connections to the batteries. So then we come out here and we go to this inverter here, and then of course we're coming to this wire here, and we're going to this 60 watt bulb, and I can turn it off for a minute because it's quite bright, and you can see the 60 watts. So you can see as I turn it off, the voltage in the battery is going to go up, and here's the amperage. Pretty much holding its place, so it's kind of self-regulating there. So this is the basic system, battery swapping and all. Now we wouldn't want to do it like this. We want to definitely have this at 1 hour intervals, and there you go. So now we could use an external generator here as well and pull this down more so that we're at, you know, like 8 or 10 amps, and pull it more. But I thought this is quite interesting that I am producing, I mean, there's quite a bit of losses right here with these clips and all that. I am producing a good 80 watts worth of energy here, because these are not more than 80% efficient, probably like 65 or something like that. So, well, yeah, what I wanted to do is turn this off and look at the position of the Hall. So I put the little dots where the magnets are, so you could see this is the startup Hall, and they're actually pretty much in the same position, so I really don't need that at 12 volts. And I was running it pretty much the same place at 24 volts. So this is the run Hall. So this runs first for so many magnet passes, about I think 500 or something, and then it clicks over to this one. So this one is quite sensitive if you move it, if you advance it or retard it, and you've got to be really careful with it, because, oh wait, let's turn this off. We don't want to be running that battery down off of you know, when it's not running. So you can see the voltage is bouncing back here on this battery, and that's just a 14 amp hour battery right there. Let's move this thing out of the way. So you know, like there's a voltage drop, of course, under load, and so that's what you're experiencing there. And you have to consider that in your run here. Now, of course, this has gone to 0 because we've got no no load on it at all. And then we can look at some of the voltages here with this cookie meter that has, so 1264 on that battery. And if we go over here, so we've connected that one there and that one there, and we're at 12 volts there. So yeah, so again, what you want to do is run these more in you know, longer time intervals. At least the shortest, or the most, sorry, the shortest would be 1 hour intervals, and ideally it'd be like, you know, 5 hour intervals. You don't want to actually make it too long, because you don't want the voltage to drop too low, because it will affect the RPM. You could see there's about a half a second of switch time between the rotation of the batteries, which I probably want to shorten that a little bit, because while this is under a load, it just really clamps down and drops the RPM quite a bit. You don't notice that really on the bigger motor, because it is got a much bigger flywheel on it. So for this little one, if we had a lighter load on it, it would not notice it as much, and if it was spinning faster. But yeah, if you don't have this quite set up right, then it could blow out the MOSFET. So you really want to put, you can see that's cold, it didn't get hot. We're not really doing much with that at this point. And we have all these protections on it right now. We're keeping it under the 100 volts on the spike with the oscilloscope here. We're looking at that as we did in another video, or earlier in the video. And so we want to keep that voltage lower than the maximum, being 100 volts.
so to protect that diode and to protect the device in general. So yeah, so again, there's the timing approximately, and I think we can pretty much get away with the one Hall on this smaller motor. We don't really need the double Hall system. But you know, if you want to start it up, you can see if you move it over one way or the other, it's going to start up faster, so that you kick up that RPM, and then you get to that run RPM. And now because it's under load, it's actually a lower RPM, and so there is a different timing. So as we go up higher and higher, we could advance it a little bit, or actually, yeah, no, retard it a little bit. Oh no, it's advancing it, sorry. We're turning it clockwise here. And then we could move it over, it'll speed up faster, and you can watch the amps and all that. I wasn't going to try and explain all that while it was running, so that you know, people could hear you know, what I'm talking about, because people have complained about lack of proper microphone. So anyway, let's look at a couple other things again. This is the driver for the latching contactor here again, and this is 2 MOSFETs, 2 diodes, and that's it. And so you have the Arduino on either side of the jumper here, pins 3 and 6. Pins 3 and 6 are going to the MOSFET, and you can see the diagram about that. And then the output, yeah, the output is going into rotating each solenoid here every 5 minutes in this case, but it will be an hour normally. And then you've got one negative terminal going to the common negative bus underneath the board, and then these are just the Hall wires here, of course, and there are pin number 2 is the startup battery, or startup Hall, and pin number 7 here in this case is the run on this side. And then let's see, so this has worked out okay. Ideally you want short wires going to the charge battery, thick wires, I mean as thick as you could possibly imagine, will give you the best results. And you want solid connections, not these clips here. I don't know what people are going to have on their terminals to their batteries, so it's up to them to do that, make good connections on, especially the, well, they're both going to be the charge side because they're going to rotate between each other. And then again, I'll say with this Arduino battery, you know, mistakes happen, and I made a major blunder. I had my accessory battery, actually it was this one over here, run. You know, you have to learn from my mistakes too. I make mistakes because I'm kind of running around doing different things and using batteries for all sorts of things. And this battery, well, I had one set up, the larger motor running, and it had worked at my convention, and I brought it back to the shop, and it didn't work. And I was like, well, what's going on? So I'm trying to figure out, looking at the circuit board, looking at everything, making sure everything's connected, see if a wire is broken or something, you know, and moving things around that can happen. And I replaced the Arduino board and everything. I was trying to figure it out, and then the same thing happened, and I was like, well, this doesn't make sense. And after all this fuss, I realized that the input battery was at 8 volts. It must have been, something must have happened when I was doing my other experiments, and I actually damaged the one board when I was doing the MIC coil at 24 volts. It exceeded the voltage maximum on the MOSFET, and I damaged the FET. And I think what happened is it shorted out the input battery and it discharged it, and I didn't realize it. Anyway, these things can happen, and when that voltage goes down there, it can actually cause a big problem. It doesn't take much to keep it charged because you're only running, milliamps of power to run the Arduino and the gate driver, and that we can see that when we do the resonance induction kit, which is doing the same sort of thing, the gate driver. So just a couple of points there. Now, the other thing I need to mention is, well, let's just disconnect all this. Again, the system will always start off with battery bank A. I don't have any other option at this point because the battery is, though the code is set to always start with one particular bank, it doesn't measure it or anything, so it just rotates it. Anyway, you have to keep that in mind if you're starting and stopping this. This is when you activate this jumper here, it turns on the battery rotating system, which will, every hour, in this case it's 5 minutes that I've set the code to, but every hour normally it will switch, whether you have these components on it or not. It will stop the motor, well, it will turn off the motor for half a second. So you'll see that whether you have this connected or not when you have the jumper on there. So anyway, that's something to keep in mind. And don't connect this, I've said this before, don't connect the Arduino or disconnect it while it's running and then try and reconnect it while it's still rotating, because it will give you a pulse, the initial pulse, and that's not good. It'll be like electromagnet there. Anyway, the other thing is I have set this, in this case I have the potentiometer almost all the way turned up. I think it was all the way up. Anyway, so that's full, and you want to start off with that lower until you get used to it, and then make slight adjustments there while you're positioning this. So I'm showing you that right now so that you can make sure it's there. If we've shipped it assembled, it could get moved around while you're unpackaging it, so it gives you an idea of where to position it. You don't have to put the dots on there like I do, but I just wanted to do that for this video. And normally, if there's only one hall, it will be just on the pin number 2 on the Arduino here. So you can, in this case, it's pretty much the same thing, so there's really no need for 2, as I said. So yeah, if you turn this, we have a timing in the code that's a percentage, in which if you go to higher voltages, then we need to turn down the percentage of on time. And so you could do that again by pulling this hall out further away, so that it has less of an on time. If you think of the magnetic field like this, and you're just getting on the bottom edge of it. So when you go up to 24 volts, you have to go up in stages. If you're going to load this thing down or let it freely spin fast is going to be a different timing here. So that's where you have to consider that. If you turn it down some, then you can have more flexibility with different kinds of loads, but you'll have lesser maximum amperage. And then of course we're not getting into 36-48 volts right now with this kit, because we have to set the code back a lot smaller. So we really are going to make code available for 12, 24, 36, 48 volts, and we'll just provide the chips. In this case right now we've got the boards, and they're just like $5 a piece. The blue board, the Arduino board underneath here. Well, here's one over here somewhere. So if we have that, now I want to get these chips as soon as I can source a better source for these, so that I can just provide those for like $2 or something. We are not going to give out the code for various reasons, as I've explained before. So yeah, it's a matter of timing. So it's a matter of the Hall timing, the code timing, and the potentiometer timing. And they do essentially, the three of them do the same thing, depending on, you know, the position of the Hall and turning this. So clockwise in this case is turning to the maximum. So yeah, there you have it. This is just one type of load output. This is not showing the MIC coil. We had it on this setup earlier, and it was okay for 12 volts, but once you go above 12 volts, then you need to have a really good load on the MIC coil, so that there isn't much coming into the rest of the input system of the motor. And you have to load down the output of that. So it's very similar to the third stage process on the output side in that case. So yeah. Anyway, that's, I think, all that I need to cover here. Again, this one has the lightning arrestor in there, and the capacitor, 1 microfarad capacitor there, and a fast switching diode here. That's worked pretty good. It's 20 amps on there, so it's sufficient. And let's see, what else? Yeah, so if you're going to do this, like I said, get yourself secure clips, good sized batteries. These are 35 amp hour batteries here, and I don't really recommend these batteries because they're sealed, and if you off gas them, it's not really a good thing. You may be able to put some water back into the sealed ones. Sealed lead acid battery, but some of these ones are AGM. So this one over here, I think, is one of these. Yeah, it's an AGM battery. So you know, you have to be careful with these batteries. So ultimately the open flooded type are the best to use, and then you can always add more water to them, and you have to not have to worry about these being ruined. If you had a system like this pulling about 5 amps continuous, then it's not unreasonable to get, you know, 60, 80, 100 amp hour batteries. Now the thing about it is too, there's nothing on this right now that deals with over or under charging. So you're going to have to watch this from time to time to make sure that the batteries are keeping up you know, the system without either overcharging, which is not as serious as undercharging will stop the motor, of course, then you won't have operation. So there is no system in place for that. Now you can pull a little bit of energy off of the output. You can. This is where I was providing the MIC kit addition, which can allow you to supplement any. You could have a little bit going from a voltage regulator into one of this accessory battery, and just keep it at 13.3 or something volts. And then if you needed to add more to these periodically, you could do that too. So that's the basic system. So thanks for watching.